For years, the race to dominate artificial intelligence has followed a familiar formula: build faster processors, deploy more GPUs, expand data centers, and invest billions in computing hardware. Every new generation of AI infrastructure has been measured by the power of its chips. The assumption has been straightforward: the stronger the processor, the more capable the AI system. But as models continue growing in size, that equation is becoming less complete. Today's most advanced AI platforms rarely rely on a single processor. Instead, they spread workloads across thousands of accelerators operating simultaneously, often inside multiple buildings or even separate data centers. That shift has created a new challenge. No matter how powerful each processor becomes, the system can only move as quickly as the network connecting those processors together. If information cannot travel fast enough, expensive hardware spends valuable time waiting instead of computing. China's latest networking demonstration highlights this changing reality. Using an advanced hollow-core optical fiber system, researchers successfully transmitted massive amounts of data across a long-distance connection while reducing many of the limitations associated with conventional fiber. The achievement is significant not because it introduces a new AI chip, but because it focuses on something that could become equally important: the infrastructure carrying information between those chips. As artificial intelligence scales to unprecedented levels, computing power alone may no longer determine who leads the industry. The next competitive advantage could come from building faster, more efficient communication networks that allow thousands of processors to function as one coordinated machine. If that proves true, the future of AI may depend just as much on the speed of information as on the speed of computation itself. When people think about artificial intelligence, they usually imagine processors performing billions or even trillions of calculations every second. While that computing power is essential, it represents only one part of the process. Modern AI systems spend an enormous amount of time moving information between processors, memory, storage devices, and networking equipment. Every calculation depends on data arriving at the right place at the right moment, and as AI models grow larger, that constant flow of information becomes increasingly difficult to manage. Training today's most advanced AI models requires thousands of accelerators working together as a single computing platform. Each processor handles a portion of the workload, then continuously exchanges model parameters, intermediate results, and synchronization data with neighboring processors. If one part of the system falls behind, the others often have no choice but to pause and wait. As a result, even the world's fastest processors cannot operate at full efficiency when the network connecting them becomes the limiting factor. This challenge becomes even more significant as AI infrastructure expands beyond a single server or building. Many technology companies now distribute computing resources across multiple data centers because of power availability, cooling requirements, and physical space limitations. Those separate facilities must still communicate almost as if they were one machine, requiring enormous bandwidth and extremely low latency to keep thousands of processors synchronized. That reality is changing how engineers think about AI performance. For years, improvements came primarily from building larger chips with more computing cores. Today, however, communication efficiency is becoming just as valuable. Faster networking allows processors to spend more time performing useful work instead of waiting for information to arrive. In other words, improving the movement of data can sometimes deliver greater real-world performance than simply adding more computational power. As AI systems continue scaling, the network itself is rapidly becoming one of the industry's most critical pieces of infrastructure. Against this backdrop, a recent networking experiment from China attracted attention not because it introduced a new processor, but because it targeted one of AI's growing infrastructure challenges. The project was carried out by Yangtze Optical Fiber and Cable, commonly known as YOFC, in collaboration with China Telecom and optical equipment manufacturer Decole. Together, they demonstrated a long-distance optical transmission system designed to push the limits of modern networking performance. According to the reported results, the team successfully transmitted an aggregate 51.3 terabits of data per second across a distance of more than 200 kilometers, or roughly 128 miles. Individual optical channels reportedly reached speeds of 1.2 terabits per second, while the complete system maintained stable transmission across the entire route. For network engineers, those numbers are significant because they combine high capacity with long-distance operation, two goals that are often difficult to achieve simultaneously. However, the most interesting part of the demonstration was not the transmission speed itself. It was the communication medium carrying the data. Instead of relying on conventional solid-core optical fiber, the researchers used hollow-core fiber, a technology that guides most of the light through an air-filled channel rather than solid glass. Although the cable is still manufactured using highly engineered glass structures, dramatically reducing the interaction between light and glass changes several important characteristics of signal transmission. YOFC says this approach can increase signal propagation speed while reducing latency and minimizing several forms of optical distortion that become more noticeable at extremely high data rates. These improvements are particularly attractive for applications where enormous volumes of information must move between computing systems with as little delay as possible. The demonstration is important because it represents more than a laboratory experiment. It suggests that communication technology itself is becoming an area of strategic innovation alongside processors, memory, and AI accelerators. As cloud infrastructure grows larger and AI workloads become increasingly distributed, advances in networking may have a direct influence on how efficiently future computing systems operate. Rather than asking only how fast a processor can calculate, engineers are beginning to ask an equally important question: how quickly can the information reach that processor in the first place? To understand why this technology has generated so much interest, it helps to first look at how today's internet infrastructure actually works. Nearly every email, video stream, financial transaction, cloud service, and AI workload depends on optical fiber. These cables carry information as pulses of light traveling through an ultra-pure glass core, allowing enormous amounts of data to move across continents with remarkable efficiency. Even so, conventional fiber has unavoidable physical limitations. Although light travels incredibly fast, it slows down when passing through solid glass because of the material's optical properties. In standard silica fiber, signals travel at roughly 2/3 the speed they would achieve in a vacuum. For everyday internet use, that difference is almost impossible to notice. But when AI systems exchange massive amounts of information across hundreds of miles, even tiny delays accumulate into measurable latency. Another challenge appears as transmission speeds continue increasing. As stronger optical signals travel through glass, they begin interacting with the material itself. These interactions can create distortions that reduce signal quality and make it harder to transmit more data over longer distances. Engineers have spent decades developing techniques to minimize these effects, but they remain one of the fundamental constraints of conventional optical networking. Hollow core fiber approaches the problem from a completely different direction. Rather than sending light through a solid glass center, it guides most of the signal through a tiny air-filled core surrounded by an intricate microscopic glass structure. That surrounding structure acts as a carefully engineered pathway, keeping the light confined inside the hollow region while minimizing contact with the glass itself. Because the signal spends far less time traveling through solid material, it can move closer to its natural speed while experiencing less distortion along the journey. Reduced interaction with glass also improves signal integrity, making it easier to support higher capacity transmissions over long distances. In simple terms, the technology is not changing the information being transmitted, it is changing the environment through which that information travels. The concept itself is not new. Researchers have explored hollow core fiber for many years, but early designs suffered from excessive signal loss, making them impractical for commercial deployment. Manufacturing techniques have gradually improved, allowing engineers to dramatically reduce attenuation while preserving the technology's low latency advantages. That progress is what makes recent demonstrations particularly important. Instead of proving that hollow core fiber is theoretically possible, they suggest it may finally be approaching the level of performance required for real-world communication networks. As impressive as the reported results appear, they are easy to misunderstand without looking at the technical details. Headlines often reduce complex engineering achievements into simple claims, but the value of this experiment lies in what it actually demonstrated, not in what people assume it proved. The first point to understand is the reported 51.3 terabits per second transmission rate. That figure represents the combined capacity of many optical channels operating simultaneously, not a single stream of data. Modern optical networks use a technique called wavelength division multiplexing, where multiple colors, or wavelengths, of light travel through the same fiber at the same time. Each wavelength carries an independent flow of information, allowing one physical cable to transport an enormous volume of data without requiring additional fibers. Another important detail involves the phrase "without electronic regeneration." At first glance, this can sound as though the optical signal traveled the entire distance without any assistance. In reality, that is not what happened. The system still relied on optical amplification to strengthen the light as it moved across the network. What it avoided was converting the signal back into electronic form, cleaning and rebuilding the data, and then retransmitting it optically along the route. That distinction matters because electronic regeneration introduces additional equipment, higher power consumption, greater operating costs, and small amounts of extra latency. By maintaining the signal optically across the full transmission span, the researchers demonstrated that long-distance communication can be achieved with fewer interruptions in the data path. For large-scale infrastructure, reducing the number of regeneration points can simplify network design while improving overall efficiency. The experiment also showcased sophisticated management of individual optical channels. Rather than treating every wavelength identically, The system dynamically adjusted transmission parameters to match real operating conditions. This type of optimization helps maximize total network capacity while maintaining reliable signal quality across long distances. Taken together, these achievements make the demonstration significant from an engineering perspective. It was not simply about reaching an impressive speed record. It showed that advances in fiber design, optical transmission, and intelligent network optimization can work together to support the kind of high-capacity communication that future AI infrastructure will increasingly require. In other words, the breakthrough was less about a single number and more about proving that next-generation optical networking is becoming practical for real-world deployment. The importance of this technology becomes much clearer when viewed through the lens of modern AI infrastructure. Training today's largest artificial intelligence models is no longer the job of a single processor or even a single server. It requires thousands of accelerators working together across massive computing clusters, continuously exchanging information while remaining perfectly synchronized. In these environments, communication is no longer a background task. It has become a critical part of the computation itself. Every stage of AI training involves an enormous flow of data between processors. Model parameters, gradients, activation values, and intermediate results must move rapidly from one accelerator to another. If those transfers are delayed, processors cannot simply continue working independently. Instead, they often pause until the required information arrives, leaving expensive hardware temporarily underutilized. As clusters grow larger, these small delays multiply across thousands of devices, gradually reducing the efficiency of the entire system. This challenge is becoming even more important as AI companies expand beyond individual campuses. Building one enormous data center is not always practical. Electricity availability, cooling capacity, land constraints, and regional infrastructure often force operators to distribute computing resources across multiple facilities. Those geographically separated locations must still communicate with enough speed and reliability to behave as though they belong to one unified computing platform. That is where hollow core fiber could offer a meaningful advantage. By allowing information to travel with lower latency and reduced optical distortion, it has the potential to improve communication between large AI clusters separated by significant distances. Faster data movement means synchronization can occur more efficiently, helping processors spend less time waiting and more time performing useful computation. While the gains for any single transmission may appear modest, the cumulative effect across billions of data exchanges can become increasingly valuable. This does not mean hollow core fiber alone will solve every networking challenge facing artificial intelligence. Overall system performance still depends on switches, transceivers, software frameworks, memory architecture, and workload optimization. Nevertheless, improving the physical communication layer addresses one of the few constraints that cannot be overcome simply by adding more processors. As AI models continue expanding over the coming decade, infrastructure strategy may shift accordingly. Instead of focusing exclusively on faster chips, companies may invest just as heavily in the networks connecting those chips together. In that environment, advanced optical technologies such as hollow core fiber could become a foundational component of next-generation AI data centers, enabling distributed computing systems to operate with greater speed, efficiency, and coordination than today's conventional networking infrastructure allows. As artificial intelligence expands, the conversation is shifting beyond performance alone. Technology companies are now asking a second question that is becoming equally important. How much energy does it take to deliver that performance? Training advanced AI models already requires enormous amounts of electricity, and networking infrastructure has become a growing contributor to that overall demand. Every large-scale AI deployment relies on far more than processors. Optical transceivers, network switches, routers, amplifiers, storage systems, and cooling equipment all consume significant power. As organizations connect larger clusters across multiple facilities, the amount of networking hardware required continues to increase. Each additional device introduces not only higher energy consumption, but also greater maintenance costs and more potential points of failure. This is where hollow core fiber could provide practical benefits. If signals can travel longer distances without requiring electronic regeneration, network operators may be able to reduce the amount of intermediate equipment deployed along major communication routes. Fewer regeneration systems mean fewer devices drawing electricity, occupying physical space, and requiring ongoing maintenance. Over time, those operational savings could become meaningful, particularly for companies managing large-scale cloud infrastructure. However, it is important to keep these potential advantages in perspective. A more efficient fiber cable does not automatically make an entire AI network energy efficient. Transceivers still require power to convert electrical signals into light and back again. Network switches continue directing traffic between computing systems, while cooling equipment remains essential for maintaining stable operating conditions. The total energy profile of an AI data center depends on the interaction of every component rather than any single technology. The strongest business case for hollow core fiber is therefore likely to emerge in environments where network performance delivers measurable financial value. Large cloud providers, hyperscale AI operators, and organizations managing distributed computing infrastructure may find that lower latency and reduced network complexity justify the higher cost of deploying advanced optical technology. For smaller applications, conventional fiber will remain the more practical solution for many years. Ultimately, the debate is not simply about replacing one cable with another. It is about improving the efficiency of an increasingly complex digital ecosystem. As AI infrastructure continues to expand, technologies that reduce operational overhead while helping expensive computing resources stay fully utilized may become just as valuable as the processors those networks are designed to connect. Although China's demonstration has drawn considerable attention, it should not be viewed as an isolated breakthrough or the beginning of a one-sided technological lead. Hollow core fiber has been under development for decades, with research institutions, telecommunications companies, and cloud providers around the world investing heavily in its potential. What is changing now is not the concept itself, but the growing ability to manufacture and deploy the technology at commercially meaningful scales. Several major technology companies have already recognized that future AI infrastructure will require more than powerful processors. Global cloud providers are investing in next-generation networking technologies because they understand that communication is becoming a competitive advantage. As AI workloads expand across larger data centers and geographically distributed facilities, improving how information moves between computing resources has become just as important as improving the processors performing the calculations. China's recent demonstration reflects that broader industry trend. Rather than introducing an entirely new field of research, it shows that Chinese companies are building expertise across the entire optical networking ecosystem. That includes fiber manufacturing, transmission equipment, optical components, testing capabilities, and large-scale deployment. Developing each of these capabilities domestically strengthens the country's position in a market that is expected to become increasingly important over the next decade. Manufacturing capability may ultimately prove more valuable than laboratory performance alone. Producing a record-setting fiber in controlled conditions is one achievement. Manufacturing thousands of kilometers with consistent quality is another. Telecommunications operators require products that can be produced reliably, installed efficiently, and maintained over many years without compromising performance. Success in those areas often determines whether an innovation becomes a commercial standard or remains confined to research projects. This is why the competition surrounding hollow core fiber extends far beyond technical specifications. Companies are racing to improve production methods, lower manufacturing costs, develop compatible networking equipment, and create industry standards that encourage wider adoption. Whoever solves those practical challenges first could gain a significant advantage in supplying the infrastructure behind future AI networks. Ultimately, the race is not simply between China and the West. It is a global effort to redefine how information moves through tomorrow's digital economy. As artificial intelligence continues driving demand for faster, larger, and more interconnected computing systems, the countries and companies that master advanced networking technologies may shape the next generation of cloud computing, just as much as those building the world's most advanced processors.